All right, let's talk about derivative optimization or derivative approximation, and then using derivatives as a method for optimization, finding maximums and minimums. Okay, so let's go back to the Newton-Raphson method. And in the Newton-Raphson method, we needed to have the f prime. We needed to have the derivative of the function. So we're going to say, if this is our current value, x at time n, then we find the next value by taking our current value, and then we subtract off basically the length of the run, which is found by taking the rise f of xn divided by the slope, which is f prime of xn. But that required us to find the derivative at point xn. And this could lead us to some issues where maybe we have trouble figuring out a function that's going to calculate the derivative, okay? So, if we wanted to calculate, use Newton-Raphson method for this function, log of x minus e to the negative x, we take the derivative, 1 over x plus e to the negative x. And that was simple and straightforward, and that worked out just fine, right? We could plug in at the value 5, what is the derivative? Okay, so the value of the function at 5 is 1.6027, and the value of the derivative at 5 is 0.2067, okay? So that's fine, okay? And here's the plot, the value of the function, what was it, 1.6027, and then the value of the derivative, if you calculate the derivative, that's 0.207, okay? So figuring out the derivative of that function was straightforward, but sometimes you're in a situation where figuring out the derivative of the function can be difficult. And so in those cases, we can approximate the derivative, okay? We can approximate it. And basically, we just use the definition of the derivative to figure out how we're going to approximate it, okay? So the definition of the derivative is that you calculate, the value of the function at some point a, and then you add a tiny little h to it, right? So you say, okay, we're going to add h to a, and we say, okay, well, what is the value of the function there? And then we say, okay, well, how much did the value of the function change from a to a plus h? And so you say, okay, well, that's basically the difference, the change in the rise, and then divide by, how much did you add to a? That's going to be h. And then as h goes to 0, that's going to give us the definition of the derivative. Okay, the derivative is as h goes to 0 of this thing. And so a numeric approximation is we're going to just take this equation here, and rather than trying to figure out the limit as h goes to 0, we're just going to plug in a really small value of h. Okay, so here my approximation, I might plug in, say, 10 to the minus 6 as my value of h. And so here's my value function. My function is f of x. That's log of x minus e to the negative x. And now I'm going to add a little h to x. So I'm going to get log of x plus h minus e to the negative x plus h. And here h is 10 to the minus 6. I'm going to say, how much did the value of the function change? What is value of f of x plus h minus f of x divided by h? And so when I plug that in, and I say, hey, give me 12 digits of precision here, all right, what R calculates is my approximate derivative is 0.2067379236669, okay, versus the actual value of the function when I did, 1 over x plus e to the negative x, and I plug in 5 there, I get 0.20673794699, okay, and so we can see it is accurate up to 7 places after the decimal point, okay, so 0.2067379, that's accurate up to there, and these last few digits differ, but I'd say this is a pretty good approximation, and all we did was we just asked the computer to calculate the value of the function at 2 locations, and we took the difference and we divided by h. And so there the way I calculated the value of the derivative was I added a little h here. What if I add a negative value of h? So instead of adding 10 to the minus 6, I subtract off 10 to the minus 6. Okay, so same kind of thing. Calculate the value of the function at x, value of the function at x plus h, and I say, all right, how much did the value of the function change? Divide by the size of h, okay? And what we get here is we get, a slightly different value. Again, it is precise. We have the first 7 digits after the decimal place align, but this number is different. So if the true value, so this is the true value by plugging in 1 over x plus e to the negative x, I get this. And if I plug in, use a negative h, I get after the 9, I get a 70299. And then when I plugged in a positive h after the 9, I got a 2366. Okay, where the true value after the 9 was a 4699. Okay, so this value using the negative h, the left, this is kind of like finding the derivative as h goes to 0 from the left-hand side. This approximation is just a little bit bigger, right? 7 is bigger than 4. And then over here on the right-hand side, coming in to h goes to 0 from the right-hand side, it's a little bit too small, okay? And that's because there's a little bit of curvature, all right? And so the left-hand approximation is a little too steep. The right-hand function is a little too, or the right-hand approximation is a little bit too shallow, okay? And so, one way to kind of correct for this is we can take the average between the left and the right-hand side. I've got this graph illustrates it, okay? So here, the true tangent line is this dotted red line, okay? And here I'm using a very big h, an h of positive 1 and an h of negative 1. And so the green line is the right-hand side. If I add a positive h, okay, in green, the function runs through the line runs through the function at 5 and at 6. And so you can see because there's curvature here, the green line, its slope is a little too shallow. And then the orange line, it runs through the point 4 and 5. Its slope is a little bit too steep, okay? And so you can see, all right, well, the dotted red line, which is the true tangent line, is somewhere in between the slopes of the orange and green lines, okay? And so here, kind of my balanced approximation function is I'm going to calculate f when I do x plus h, and I can calculate f when I do x minus h, okay? So now I've got basically a difference there. I can say how much did the function change when I added h to it, how much did the function change when I subtracted h, and then and then I'll divide by 2 times h because that's going to be the difference. And then so now when I use this function to approximate my derivative, we can see we have lots of decimal places of precision. I think it's accurate to 10 places after the decimals. So the true value being 206,737,946,999, and here I get 206,737,946,984. So just the 11th decimal place is off, and it's only off by a little bit. So this is a pretty good approximation of whatever r is calculating, okay? And so here I've been using the same function here, log of x minus e to the negative x, but here I can kind of generalize this, and we will allow it to just calculate. One of the arguments will just be some generic function. And we're going to say, all right, this is the location where you want to find your derivative. And then we're going to plug in, what is the h size of the h? And so my default value is going to be 10 to the minus 6. But perhaps if you have larger numbers, you want to use a larger h. If you have smaller numbers, you can use smaller h or something like that. So I'm going to calculate, okay, what is my left side value? That's going to be x minus h. What is my right side value? That's going to be x plus h. And then we're going to calculate the function on the right side value. We'll subtract off what is the value of the function on the left-hand side, and we'll divide by 2h, okay? And whatever that is, this will be a way to kind of generalize our numeric approximation to the derivative, okay? So this is just calculating the value of the function at 2 locations and then taking the difference in f and dividing by the size of the difference there. So that's going to give us a numeric approximation to the thing. So here I'll write my function as log of x minus e to the negative x, and I can plug in, you know, what is the derivative of f at, you know, 5 locations at location 5, and we get this. Here's another option. Okay, so here my function is going to be x squared. Okay, and then and so what is the derivative of x squared at 5? Okay, the derivative of x squared at 5 is going to be 10, and I can say, okay, give me my approximate derivative, and it says it's 10. If I say give me 12 decimal places of precision, we see it's not exactly 10. It approximates it, and it says it's 10.00000000014. So I think we have 1, 2, 3, 4, 5, 6, 7, 8. It's accurate up to 8 places after the decimal, and then it's off by 1 there. Okay, and so that's what we have. Now, you might say, well, you know, the h that you've been using is 10 to the minus 6. Okay, 10 to the minus 6, and then as far as the definition of the derivative goes, it's the limit as h goes to 0. So why don't we just choose a really small value of h? Why don't I just choose a really small value of h? Okay, well, what happens is if you use too small of an h, then you run into the problems with floating point numbers. So remember, as far as floating point numbers go, the computer is really only able to keep track of, like, 16 significant figures, right? You have 52 bits in the mantissa, and that corresponds to around 16 decimal places of precision here. Okay, and if you have bigger numbers, then, you know, 16 significant figures might correspond to a really big number. Okay, so here I just kind of want to show you the effect of choosing slightly different, you know, values of h. So here, if I have 5 and I do h is 10 to the minus 5, this is my approximate derivative. Here I'm saying print out 16 decimal places. So the true value is 10, and here I get 9.999999996. Okay, if I use h as 10 to the minus 6, I get 10.00000000139. At 10 to the minus 7, I get 0.000000028. Okay, so I actually have less precision. At 10 to the minus 8, I have 9999999, and you can see I'm off by 1, 2, 3, 4, 5, 6, 7, the kind of last 7 digits out over here. So here I'm off by the last 6, off by the last 7, and so, you know, the amount we go off gets bigger and bigger. At 10 to the minus 10, I have fewer decimal places that are accurate. 10 to the minus 12 for my h. You know, now I'm only accurate to 10.0008, right? I only have 3 places after the decimal where it's accurate, and then we start getting a mismatch. And at 10 to the minus 14, okay, I'm getting, my values are, you know, I'm off, right? 9.76. 10 to the minus 15, I'm off by even more, 8.88, right? And so you have, and then at 10 to the minus 16, now my derivative is 0, right? Because basically, when if my base number is 5, I'm actually not even able to add 10 to the minus 16 to it, because I think computationally R sees, or the computer sees, the value 5, and 5 plus 10 to the negative 16. I think it sees it as the same number. I could be mistaken, but you know, if I say x is equal to 5, and then I say, what is x? I'm going to say y is going to be x plus 1e minus 16. Okay. I'm going to ask, is x equal to y? And it is. Okay. So the computer is not able to tell the difference between 5 plus 5 to the negative 16. Let me try, you know, here if I do, you know, x plus 10 to the minus 15, okay, is x equal to z, it's able to distinguish between these two, okay? But trying to add 10 to the minus 16 to 5, the computer's not able to distinguish between x and y here, okay? So this is why it's important to understand floating point numbers and understand kind of the limits of, floating point arithmetic. And so, you can't treat it like real numbers where you can just kind of keep shrinking h. The idea of h going to 0 just doesn't work. And so we actually get our most accurate results when h is something, a little bit more reasonable, like 10 to the minus 6, at least when the number here is 5. Again, if the numbers say like 100, okay, then you probably need to have something bigger. Maybe 10 to the minus 5 or 10 to the minus 4 is going to be a more reasonable number to use when you have something like x being 100, okay? So anyway, it seems that using a value around 10 to the minus 6 is a good choice. When h is 10 to the minus 14, the accuracy drops dramatically, and then the calculation returns 0. When h is 10 to the minus 16, it's just not even able to do it at all, okay? But we have a way to approximate derivatives, and now that we can get derivatives, we can also use that to do derivative-based optimization. So far we've covered quite a few root finding methods, okay? And but an important idea is how can we find not just the roots, not just where the function is equal to 0, but can we find the minimum or a maximum, a local min or a local max, okay? Now, when we talk about numeric optimization, most of our algorithms are written to find local minimums, okay? And if you want to find a local max using the same algorithm, all you do is you just multiply your function by -1. And then you say, all right, I'm going to find the minimum of negative f of x, and that's going to be the equivalent to finding the max of f of x. And so the way we can take our root finding methods and use that for optimization is all we have to do is we say, well, if this is the function I want to optimize, f of x, we will find the derivative of f of x, okay? And then you take any of the root finding methods we've learned to find the roots of f prime, okay? So if you find the roots of the derivative, those will correspond to kind of critical points, and you evaluate those critical points, and those will either correspond to a local min, local max, maybe a saddle point, but that's what we'll do. So we calculate the derivative, and then we apply a root finding method to find where that derivative is equal to 0, and those will correspond to either a local min, local max, or something else, okay? So let's say we want to do it for Newton-Raphson method, okay? So what we want to do is we want to find the roots of f prime of x, okay? Find the roots of f prime of x. So we're going to start at some arbitrary location, x0. We're hoping that's close enough to the local min or local max, and then we just find the next value. So rather than saying, okay, what is f divided by f prime, now that we're dealing with the derivative, we're going to do f prime divided by f double prime, okay? And then when f prime, when the slope itself is close to 0, that's when we'll stop, right? So the issue here is that our function needs to be twice differentiable, and then this denominator part, okay, it can't be 0 for any of the xn values that we do check, all right? Now the second derivative is allowed to be 0 as long as it is not 0 for one of the locations that we check kind of in our iterations. So that's how it can go. So for example, let's say here is the function that we want to find a min or max of or something, okay? So my first derivative is going to be x cubed minus x, and the second derivative is 3x squared minus 1. So I'm going to just start off at some kind of arbitrary location, all right? So this is what the original function is, and we want to find kind of local mins or local maxes, and so we'll find the roots of the derivative, and where that derivative is equal to 0, that will correspond to either -1, 0, or 1. So just kind of applying it. Here we're going to say, okay, here's my function for f prime, here's my function for f double prime. We'll start off at 2.1, and then our next location is just take our old location, subtract off f prime divided by f double prime at the old location, okay? And so if I run this, starting off at 2.1, I end up at 1, okay? So starting off at 2.1, it runs and it ends up at 1, okay? If I start off at, say, 0.9, okay, it also ends up, right around 1. Again, these are approximate answers. You get 1.00000 something, a bunch of zeros and a 308, pretty much 1, okay? Here, if I start off at 0.1, it gives me a value very close to 0, 10 to the minus 24, or on the order of 10 to the minus 23. That's where we quit out, okay? If I start off at x is -10, I end up at a -1. So this is just an example of applying a root finding method, that is Newton-Raphson method, to the derivative f prime, but it could be applied to any of the other functions. Okay, so if r is able to calculate the derivative based on a function, all right, and again, you don't even have to find the derivative analytically. You can use this exact function here. This is basically a computer function that gives us an approximate derivative. And you can say, hey, if this gives me the derivative, let's apply a root finding method to this function. Okay, and you just plug it in, and it works just fine. Okay, so it'll give you approximate answers, but it's good enough. So you can use Newton-Raphson, you can use secant method, you can use bisection, you could even use fixed point iteration, but fixed point iteration requires you to come up with another function so that the solutions of that thing, the fixed points of that function are equal to the roots of this thing, which is a little bit tougher. So I would say stick with Newton-Raphson, secant method, or bisection method. But again, you have a way to calculate derivatives, either analytically or using approximate derivatives, and then you use a root finding method and apply it to the function that calculates derivatives, and that will help you find critical points, evaluate those critical points to decide if it's either a local min or local max. I guess you can take the second derivative at that point if you want, whatever you need to do. But that is a quick way to begin optimizing or finding optimums of functions.